Hello everybody, this is the last online lecture of Introduction to Chemistry. It feels like it took a long way getting here, but we eventually made it. Here we go. Alkanes, alkenes and alkynes. We discussed it the last time. We learned that for alkenes and alkynes there's a limitation of the rotation that can take place around the double or triple bond, because it would require the pi bonds to break, and that leads to the formation of so-called configurational isomers. So because there is sometimes steric strain of bulky methyl groups that overlap with each other, some configurational isomers that have less steric strains are more stable than those with steric strain. But it also is up to electronic effects that control the stability of the alkenes. So if you have alkenes with electron donating plus I groups, for instance, you have higher stability than with minus I groups. Alkenes themselves act as nucleophiles in reactions, and they carry out so-called electrophilic addition reactions. So we'll talk more about this today. And the strength of their nucleophilic character is depending on what R groups you have, if they are electron withdrawing or electron donating. So let's look a little closer at such electrophilic addition reactions. Specifically, we are going to look at a reaction between an alkene and a hydrogen halide, HX, such as hydrochloric acid or hydrobromic acid. So here are our two reactants, our alkene and the hydrogen halide. So you know, halides are more electronegative than hydrogens, so you'll find a partial negative charge on the halide and a partial positive charge on the hydrogen. So I draw the molecules now here with their orbitals that are involved in the reaction. So here we have the pi orbital that's adding to the sigma orbital, and then our hydrogen halide here has a sigma orbital. But now we have to ask ourselves, what is the HOMO and the LUMO? So the nucleophile is the alkene and the HOMO is the filled pi orbital, and the LUMO is now the anti-bonding sigma orbital of the hydrogen halide. So since we have a partial positive charge, the nucleophile, the alkene, is attracted to the hydrogen halide, and it carries out such a nucleophilic attack on the partially positively charged hydrogen. So as a result, the electrons from the sigma bonds, they jump over to the halides and form a lone pair, and leaving the proton of the hydrogen behind, which then undergoes the addition to the alkene, resulting in the formation of this carbocation and a negatively charged halide. So I plot the orbitals here again, and you see now what has happened to this carbon here specifically. It was an sp2 hybridized carbon, and now it has become an sp3 hybridized carbon because it has made a new bond to the hydrogen that came from the halide, or better, to the proton, because the hydrogen or the proton that came has now been given the electron from the carbon over here, making this carbon become positively charged with a vacant or empty p orbital. And our halide anion here has a lone pair of electrons also in a p orbital. So now the reaction actually continues, because that was only step one. The nucleophilic attack of the negatively charged halide is the next step. So here we have the involvement of the filled p orbital, that is the highest occupied molecular orbital in the next step, and we have now the empty p orbital of the carbocation, which is the lowest occupied molecular orbital. So the nucleophilic attack will donate electrons from the HOMO of the halide anion to then undergo a reaction to form an addition of the halide to the original alkene. So in principle, what that means is that a new sigma bond is formed between the halide and the carbon here. That's the mechanism. Now looking at the reaction, you've seen that an alkene reacts with a hydrogen halide to form a single product molecule. That means the number of molecules decreases, and as you know, that leads to a decrease of the entropy. So delta S is smaller than 0, it's negative. However, there's also actually a decrease of the enthalpy. And the reason for that is that the new bonds that are formed are stronger than the old bonds. So it's an exothermic reaction. So looking at the original bonds, or looking at the new bonds between the carbon and the halide and the carbon and the hydrogen, those two new bonds, they are much stronger than the original halide hydrogen bond or the pi bond in the alkene. So the end, in order for this to be a spontaneous process, you remember delta G needs to be smaller than 0. It needs to be negative. But since this term is positive, since delta S is negative and the temperature term is always positive, minus a negative makes a positive number. So this makes delta G positive. Now, in order for delta G to become negative, the delta H needs to be negative, which is the case, and it is actually very negative. It's strongly negative. The absolute value of the delta H is larger than the positive value of the minus T delta S, and that makes this reaction have a negative delta G and be a spontaneous reaction. So if you remember equilibrium, now the position of this equilibrium depends on the magnitude of delta G, right? So when delta G is only a few kilojoule per mole, then you have a well-defined equilibrium. But if delta G is like many tens of kilojoules per mole, then you have the reaction really very close to the pure products. So for these electrophilic addition reactions, you have a phenomenon that's called Regio selectivity. Going back to our example, for the reaction between the alkene and the hydrogen halide, we have a polarization in the hydrogen halide that causes there to be a positive charge. Then that allows for the nucleophilic attack of the double bond, causing the sigma bond between the hydrogen and the halides to be broken, forming a proton, a positively charged hydrogen atom. So now the positively charged hydrogen atom can now add to the alkene. But the question is, where does it add? Does it add to the end carbon here, or does it add to the middle carbon, right? Both are possible. At the end, you get carbocations that are formed, and the positive charge is either located at the middle carbon if the proton added to the end carbon, or it's located at the end carbon if the proton added to the middle carbon. In both cases, the halide can now undergo a nucleophilic attack to the positive charge, leading to this addition and forming here a secondary halogenoalkane, or it could attack the end carbon, the positive charge, leading to the formation of a primary halogenoalkane. Good, so the question is now, which route is more favorable? And you probably already guess it, it must be related to the stability of the intermediate carbocation. So looking at these two, we can ask ourselves, which carbocation is more stable? Well, this one here has the positive charge at the end carbon, and we have one plus I group, one methyl group here present. But up here, we have actually two plus I groups present. Two plus I groups cause there to be more stabilization of the positive charge due to donation of electron density from the two plus I groups. And that makes this intermediate more stable than that one. And therefore, the pathway up here is favorable and the one down here not. It still happens, but to a much lesser extent. So you have more addition to the hydrogen adds to the end carbon, because then the positive charge can be located at the middle carbon, which is more stable. And that brings us to the so-called Markovnikov rule. And the Markovnikov rule says exactly what we just witnessed, that the hydrogen or the proton, it adds to the carbon with the fewest R groups. So this is the end carbon here. On the other hand, the halide, it adds to the carbon with the most R groups. So it's the one over here. That is the Markovnikov rule. So we can describe this also in terms of the Gibbs free energy of the reaction. So here are our reactants, and we have the alkene and the hydrogen halide. And now we form, through an activation energy, a reactive intermediate, our carbocation. And this here is the carbocation that is favorable to be formed, because here the positive charge is more stable according to the Markovnikov rule, unlike in the other case where the positive charge is located at the end carbon, causing a less stable and a higher energy intermediate. So at the end you get your product. In both cases the energy of the two products are relatively similar, but the main route is this one because it has a lower activation energy and a lower energy of the reactive intermediate. So there's another interesting aspect about this electrophilic addition reaction, which is the rearrangement of intermediate carbocations. So here are our two reactants, a proton, which is the electrophile, and our alkene, which is the nucleophile, with a double bond at the end carbon here and methyl groups here at this end of the molecule. You know, the nucleophilic attack takes place, the hydrogen or the proton is being added to the end carbon, and a positive charge can be found now at this middle carbon, and this is now forming a secondary carbocation, because it has here two R groups going off from the carbocation. And now a nucleophile, like our halide anion, can attack the positive charge and leading to an addition of the halide. Right? So, okay, this is a reaction pathway, nothing special so far. So, but now ask yourself, we have a positive charge here at this middle carbon in this pathway, right? So it's pretty stable because it has 2 plus I groups, but it would be even more stable if it were located here, over there, like in this example. Now we have the positive charge at the tertiary side of the molecule. And that has now happened. It's really possible because the hydrogen here, together with the 2 electrons from this sigma bond, it can shift over to the positive charge, causing the positive charge to then be located at the other side of the molecule, where it is surrounded by more plus I groups, leading to more stability of the carbocation. So it's not really the positive charge that moves, because positive charges cannot move. Like, what can move is the hydride, like the hydrogen together with an additional electron from the bond that can move. But positive charge is just a result of the movement of the hydride. So the whole process leads to the formation of this more stable carbocation, and now we call this a 1,2 hydride shift. It is based on the movement of a negatively charged hydrogen, which is called hydride. And this is now a tertiary carbocation, and the tertiary carbocation can again react with a halide, a nucleophile, causing the addition of the halide to the positive side of the molecule. And this is actually the major product, because this is the main route that the reaction proceeds. Unlike this route, because of the hydride shift, we form a more stable carbocation, and this is only formed really a little bit in the product mixture at the end. This brings me to the last reaction that I want to discuss with you, the addition of water to an alkene in the presence of acids. So here's our alkene. It's a 2-methylbutene, and we have now an acid, and that forms a hydronium ion, H3O+, a dilute acid such as HCl or sulfuric acid. And you can see, because of the positive charge of the hydronium ion, it's the electrophile, and the nucleophilic attack from the alkene leads to protonation of the alkene. So one of the protons has now been added to the alkene, and that causes there to be a positive charge, and we form also a water molecule. And now the water molecule has a lone pair, right? And the lone pair is a nucleophilic feature of a molecule. So you can have again a nucleophilic attack by the water to the positive charge, and that leads to the addition of water to the whole molecule. Now this water that is being added itself can be subjected to another nucleophilic attack from another water molecule. And the reason for that is because since the oxygen carries the positive charge now, it is very electronegative to the hydrogens, and that causes the hydrogens to become partially positively charged, very strongly partially, and that allows then the lone pair of another water molecule to carry out another nucleophilic attack, leading to the breakage of the sigma bond between the oxygen and the hydrogen, and that causes the formation again of a hydronium ion. So the proton from the water has been added to the free floating water, forming again a hydronium ion, and also the alkene that we started with has become an alcohol through these steps. So hydronium has been regenerated, and we now form 2-methylbutanol, right? So this path here, that's a major technique in the industry to form alcohols. So many alcohols, for instance, those that are used in disinfectants, they are formed by this addition reaction of water in the presence of acids. Wow, that's it. We have some homework for you guys to do. Please tackle homework problem 21.1, but only part A and B, and 21.2, and here also only part B. This is the end of our online lecture. I really hope these recorded lectures have helped you in your studying. I want to thank you for watching them and for often asking me questions via email. I'm very much looking forward to also now see your knowledge clips that you will make based on your essays. And until then, I wish you very much luck in studying, and all the best, and hope to see you soon. Best wishes.